Good morning, folks. Our section 5 introduces us to the different types of operating systems available on the market. We concluded by looking at the key ones and how they function, their advantages and disadvantages. Today's section is section 6. We're moving on to section 6, which talks about the process concept. There's a good understanding of the process concept is so fundamental to the study of operating systems that we need to take this session very seriously. I encourage you to look up the material on this topic and make sure you understand what is meant by the process concept. As an overview, the section explains the process concept and process transitions. We'll need to identify and draw and explain the various transitions a process goes through or undergoes from inception when it's introduced to the system to the completion of execution and exit. We also explain what is meant by the term deadlock in relation to operating system or the function of operating system, and we'll look at techniques that has been developed to prevent deadlock situation occurring in operating systems. The key topics to be covered in this section are as follows. We try and define the process, and we define a process state. We'll look at a 5-state process transition model. Then we'll try and explain what is meant by context switching and its relation to the function of operating systems. Deadlock, how deadlock can be detected, and some of the techniques that has been developed or adopted in real commercially available operating systems to prevent deadlock occurring. As I said earlier, the session is supported by Stalin's chapter 3, and I encourage you to make that material your own. Make sure you understand very well, you have a very good understanding of what is meant by the process concept. A process basically is defined as a program in execution, and as a process is executed, it advances or makes progress, a sequential progress from the start through the various states to completion. The operating system is therefore responsible for following activities in connection with process management, some of which are the creation of a process, the deletion of a process, and making sure that a process advances in its execution from introduction to the final execution and exit. What therefore is a process state? We will try and explain what a process state means by using the 5-state process model. A process goes through, we said earlier, a series of discrete states. When it's introduced to the system, it moves through those states as it advances in execution to completion. And the first state is new or introduction, when the process is introduced to the system. And then from the new state, it makes a transition to the ready state. And what that ready means is that if a CPU were available, then the process will make a transition to be executed. A new means the process has been stored in the memory of the computer, and ready means it's sitting in memory, waiting to be fetched by the CPU for execution. So ready means it's waiting for the CPU or for a CPU to be assigned. And as soon as a CPU is assigned, the process then makes transition from ready to a new state called running. As soon as a CPU becomes available and is assigned to the process, then the process makes a transition from ready state to the running state, which means that the process currently is being executed by the CPU, or it has the attention of the computer CPU. At that state, the process continues to be executed sequentially until it encounters an event. One of such events is when it needs an I/O request. And if in the process of execution an I/O request instruction is encountered, then of course the process will have to make a transition from the running state to waiting state, waiting for an I/O device, usually an output device, to be available so that the process can continue to be executed. On the other hand, if it encounters no such event like an I/O request, then of course it will continue in its execution until it makes a transition from running to completion and then eventual termination and exit. There is another important event that could also occur. When the process is introduced to the system for the first time, the operating system usually assesses how much time the process will require to execute from introduction to completion. And if for any reason that quantum time runs out while the process is still being executed, then of course the process will have to make a transition from the running state to a waiting or temporary waiting or suspended state. So that's 5 key states through which, sequential states through which a process goes through from introduction to the system to execution, final termination and exit. And these states, if I should summarize, are new, the first state, and then the ready state, the running state, the waiting state, and then the completion and termination state. So it is important to be able to define the process states and clearly be able to explain the events that must occur at any state for a process to make a transition from one state to another sequential state in its as it advances in its execution. Now, how then do you identify a process in an operating system? We define a process as a program in execution. An operating system is also a form of computer code. So how then do you identify a process? There is a block containing important information about a process, which is called a process control block. One of the key, very important information pieces that are contained in such a block are the process name, one, the process parents, the process siblings, the resources that is required to be able to execute that process. For instance, memory, how much memory space is required, which CPU with the process, and the specification of CPU that the process will require to run on. The number of registers, temporary storage locations within a CPU that the process will require in its execution are all pieces of information stored within the process control block. So the PCB, the very existence of a PCB, helps us to identify the existence of a process within an operating system. We said earlier that if a process encounters an I/O request instruction, and assuming the particular I/O is engaged, then it should make a transition from running to waiting state. At that stage, that process could be considered as blocked because it's just sitting there waiting until the I/O becomes free, when it can access and then move on in its transition back to running and then continue to execute. In the absence of any such encounter, the process will normally run and make a transition from running to termination and the final exit. Now, context switching, it becomes necessary for an executing or a process that is currently running to make a transition from one process to another. For the CPU to make a transition from a currently running process to another process. And it is important that the CPU remembers where it finished off in the currently executing process before it makes that transition, so that on return, it returns to the particular point within the code where it left off to continue, and so that it will not be necessary for the process to just return to start all over again. It's just like reading a page. When you're reading a page, and for instance, you read line 7 within the page, and you are interrupted, and you needed to give attention to the interrupting source, then of course you mark line 7. Then give attention to the interrupting source, and after servicing the particular interrupting signal or source, you make a transition back to continue from line 8. You do not go back to line 1 within the page to continue reading. That's exactly how context switching works. It's a technique by which the CPU can currently save the state of a running process and hand over control to an interrupting source, service that interrupting source temporarily, and then make a transition back to continue within the process where it left off. That is context switching. Now we move on to deadlock. Painfully undesirable situation within an operating system, and it is important that designers of operating systems must make every effort to prevent deadlock from occurring in any operating system. When deadlock occurs, what happens usually is that as soon as a running process encounters an I/O request, and that particular I/O is currently being held by another process, then the running process makes a transition to the block state and has to sit there waiting while the required resources are currently being used by another process. And until those I/O resources become available and are handed over to the requesting process, we have a deadlock situation. I love using the toilet latch door as a shared resource. Currently, assuming someone is using the washroom and therefore pull the latch, the door latch, so that it shows engaged, that engaged signal or piece of information is left for the attention of would-be users so that they can read that piece of information and back off until the person who is currently using the washroom finishes, then pulls the door latch in the reverse position to say open. And as soon as that signal is left, then any would-be person can read that piece of information and know that now they can access the washroom. This principle is applied in operating system to ensure that processes competing for shared resource can access it as and when it becomes available, rather than competing to create and cause a deadlock situation, which is an undesirable situation in an operating system. So folks, all of a sudden we come to the end of this section, section 6, which treats the process concept. And as a summary, we define a process as a program in execution. We went on to look at what is a process state, and we identify 5 clear states, sequential states through which a process goes through from introduction to execution. And some of these states are new or introduction, ready, running, completion or termination, and then of course the wait situation. So you may be asked to define one or number of these states using either the 5-state model. Or should I mention at this state that there is a 3-state model and a 7-state model, and I expect you to familiarize yourself with these two in addition to the 5-state. We also look at the definition of deadlock as an undesirable situation in an operating system, and therefore the use of signal, sending signal to would-be processes as help in real operating systems to prevent the occurrence of deadlock.